Okay, so the only difference between what we're going to look at now and what we've already done is we're going to look at when we have a number in front like this. So last lesson we looked at, we didn't have numbers like 2 here, or 6, or 3, or 12. So we're going to try and draw some more conclusions because it's very similar. So this time if I take a look, the root here is 1/2 and the other one is -3. The leading coefficient that's introduced now, like I said, is 2. So if we look at the product of the roots, it's -3/2. Okay. Let's take a look at another example and then we'll see if you can draw any conclusions. So in this case, it's going to be 2/3 and -3/2. The leading coefficient is 6, so I get a -1 for the product of the roots. Do another one, or do you see a pattern there? Sure.
Take the first number divided by the coefficient, and you get the product of the roots.
Yeah, you might not see that, but for example, -3 divided by 2, that gives us -3/2. And -6 divided by 6, that gave us the -1. Okay, so I'll finish this one here. This would be 2/3. I'm going to run out of space. -3 and 1. Oh, don't go to sleep. There we go. -3 and 1. So leading coefficient this time is 3. I'm going to multiply all of these together. That's going to give me -2. And one more time down here, this would be 4 2/3 and -5/4. So if I multiply all those out, that means I'm going to get, looks like -10/3. Oops, sorry, wrong place. Let me fix that. -10/3. And we said the leading coefficient this time is 12. So how did I get 10/3? That doesn't seem to fit the pattern we were talking about. Does it?
It does.
How come?
40/12 is 10/3.
Yeah, it's simplified. 40/12. If I went like this, 40 divided by 12, it's going to give me 10/3. Okay, so the pattern is very similar to what we've talked about. It's going to be the leading constant, the constant divided by the leading coefficient. So -3/2 in this case, -6/6, and 6/3, and 40/12. So here's the rational roots theorem. So if we know that there's a leading coefficient that we're calling A, and a constant term C. So again, it's probably easier to see the example, but basically what we're saying is that if it's going to be a factor, then it must be the constant term, which is the last part divided by the first part. So again, it's easier to see it in an example. It's kind of like mumbo jumbo when you read it in math. But here's what the words up there mean. I'm going to take a look at the factors here. Okay, the factors of 3 could possibly be a 1 or a 3. And remember, it would be plus or minus because we've got to include them all. Okay. If I was dealing with 5, the factors would be 1 or 5. And again, just remind yourself, they could be positives or negatives. Okay. So what I've done on this top row, this is the constant term here. And this is the leading coefficient here. So the reason I've made it into a table is you can kind of organize your thoughts. It's going to be the constant divided by the leading term, which gives me a 1. 5 divided by 1 is 5. 1 divided by 3, it could be a third this time. And 5 divided by 3, it could also be 5/3. So we have a few more things to consider, because before the leading term was just 1. So that means we only had this row, right? We didn't have everything else. So it expands the search out. And again, you're not doing yourself any favors if you start with something. I mean, it might work. Who knows, right? 5/3 might be the one that you pick. It might work right away. But I would probably start with the easy ones before I went there. So let's see here. What am I going to write down in this column here? What would I put in for these 4? Somebody further back. I haven't heard from the middle part of the class today. Karen, you want to take a stab at it? Yeah, excellent. So 1, 2, 3, and 6. Those come from the leading coefficient. Okay, then this is my constant term here. So what would I put along the top? Andy?
1, 3, 5.
1, 3, 5, and 15. So it goes constant divided by leading. So these are the numbers that are going to appear. 1 half, 3 halves, 5 halves, 15 halves, 1 third, 1, 5 thirds, 5, 1 sixth, 1 half, 5 sixths, and 15 out of 6, that'll be, let's see here, if I take out a 5, that'll be 3 halves. Right. So, as I said, there's still a lot of choices. The difference this time, however, is we're dealing with fractions. So, let's try one.
So that was supposed to be 5 over 2.
Sorry, oh yes, it should be 5 over 2. That is a 5, it's just really messy. Can you tell?
It says 3 halves.
Did I?
Yeah.
I was just testing you then.
Yeah, okay.
Okay. Leave me alone, I have a cold.
So if you do that, you don't check every all
Well,
of the 16 numbers.
There's a factor in this polynomial, and it must be one of these numbers here. Okay? It doesn't mean you have to look at every single number to find all the factors, right? But it's going to give us a place to start. So what you have to realize too is that, you know, if you were to do this if you were to do this for real, you know, like I'm talking like if this was in a university or something like that, you know, you have a method, you'd probably teach a computer to search for these, right? It's pretty easy to teach a computer how to look for the factors of the constant and the factors of the leading, and then a computer would go through and search each of these and find it for you, rather than having to do them all by hand. But lucky for you, you're still in grade 11 and you don't have to worry about university just yet. Okay, so now, again, just to illustrate a point, you should try to pick the easy ones. So let's just see if we can find a single possible factor. As I said, if it helps to organize, you may want to use this table like I was doing. So there'll be 1, 2, 4, and 8. So in this example, if we wanted to find a factor, I would suggest that you start with this row here and cross your fingers that you can get it on the first row of whole numbers. But if not, it means we'd have to move down. So let's see if you can find one of those factors now using the rational roots theorem. So, did anyone have any luck?
X plus 2.
Plus 2? Okay, good. So don't forget here, we're always looking at plus and minus ones. So we could be checking plus or minus 1, plus or minus 2. So one possibility that we found was, negative 2 works?
Plus,
Yes, -2.
x equals to negative 2.
Okay, so if we put this in as negative 2, that means it worked. So x plus 2 is a factor. I found also it would work for, I've just cleared my calc, I think 4. I think it also, did it work for 4? Did anybody else have? Okay, so it also works for 4. So that means x minus 4 would be my value. Okay, so again, try it on this one. Look for the easy values first. Hopefully you can find one without too much search. Okay, so for this particular example, did anybody come up with some roots so far? Still punching away? Okay. Okay, so I'll just put our choices up here in case you're still working it out. Looks like 1 and 5 will make up that row. And 1, 2, 3, 4, 6, 8. Sorry?
X equals to negative 2.
Yeah, that'll be one of our roots that works here. 12 and 24. So the first row is the friendliest. So this is where I would start our search. And remember, don't forget, you're looking for both the plus and negative choices. I found a couple roots. One of them I found worked at x equals -2. Another one that I found worked at x equals 3. So some possible factors would have been x plus 2 or x minus 3 would also have been a good choice for you. Okay? Of course, if we wanted to, you could go and torture yourself into doing all the work with fractions here. But it just goes to show you that you're not totally stuck doing fractions. It does often work for the whole numbers too. Okay, so one last one. We won't bother with this. I know I'm torturing you enough as it is, so we'll just do one last question there. See if you can find a single factor.